I'm going to talk briefly about two important medical imaging techniques that are related to electricity and magnetism. These are X-rays and MRI. So first I'm going to talk about X-rays. And the term X-ray refers to a very short wavelength electromagnetic wave. So that is the name of the wave. It's a very short wavelength electromagnetic wave. And it's somewhere on the order of 1 picometer, so that's 1 times 10 to the minus 12 meters. And the way X-rays work to image tissue is when an X-ray encounters biological tissue, some of that X-ray passes through, and some is absorbed by the tissue. And different tissues absorb these X-rays at different rates. So what they do is they emit X-rays on one side of the person, and then they have an X-ray detector on the other side of the person. And based on how the X-rays are transmitted through and how they're absorbed by the materials, people can figure out what kind of tissue the electromagnetic wave has passed through. So the amount absorbed says something about what type of tissue it passed through. Okay, so then one question is, how are these X-rays produced and transmitted? So we're going to talk about how X-rays are produced, and then also how they're directed, sent in the direction that people want. And so in order to produce X-rays, here's what happens. So there is a cathode, and an anode, and that's a positive electrode. This cathode is usually created by heating up a material to free electrons from the material. And so the material in the cathode is heated up, and that frees electrons. So then we have all these free electrons around the along the negative electrode. These electrons that are freed into a space with a very high electric field. So there's a large electric field. That directs these free electrons toward the anode. When these electrons hit the anode at a very high speed, because we have this large electric field that's accelerating these electrons to a very high speed. They hit the anode, not the cathode. It releases energy. And some of that energy is in the form of these high energy X-ray electromagnetic waves. Okay, so some of that is in the form of X-rays. What about all the other stuff? So what they want is to send very high energy X-rays through the tissue. They don't want to send any low energy X-rays through the tissue because it doesn't do anything for imaging, but it does cause a danger of radiation poisoning. And so they also have materials in there that absorb a lot of the lower energy electromagnetic waves. And so what they get is a pure number of high energy X-rays. And then they bounce these off of a parabolic shaped shield that directs this flow of X-rays exactly in the direction that they want it. So they use this parabolic shield to direct the X-rays. Now that these X-rays have been focused through the body tissue that they want to focus it through, the detector on the other side can pick up how much of that X-ray passed through, how much was absorbed by the material, and then use that to produce an image. So that's the basic idea of how X-rays work. What about MRIs? Okay, so it stands for magnetic resonance imaging. And the way this works is because of sort of a quantum mechanics effect that we haven't talked about. So I'll just say due to a quantum effect, the positive charge in protons produces a magnetic field, obviously a very small magnetic field. And so if you expose, if a proton is subjected to a high magnetic field, a large magnetic field, it becomes oriented in a certain way because of the interaction of those magnets. Just like if you have two strong magnets on the table and you put them near each other, they're going to affect each other's behavior. They'll reorient each other and stick together, that kind of thing. So when a proton is subjected to a large magnetic field, it aligns in a specific way. Okay, so the part of the body that you want an image of is subjected to this large magnetic field. So they put the part of the body in a large magnetic field, which has the effect of aligning all of those protons. And the ones that they're looking for specifically are protons in hydrogen atoms. Then, when all of these hydrogen protons are aligned, a strong electromagnetic wave is sent into the body, and it knocks the protons out of alignment temporarily. Then when the wave stops, when that wave is removed, as you would imagine, those protons still subjected to that magnetic field realign. They move back to the alignment that they had before the wave was sent. And when they realign, it releases energy. That can be detected. Based on how much energy is released, so based on the amount of energy that's released, it can be determined what type of molecule these hydrogen atoms were a part of. And so, if you can figure out what types of molecules these hydrogen atoms are a part of, it goes a long way to allowing you to figure out what kind of tissues are present among all of those protons whose behavior you're looking at. One important thing about these two imaging techniques, for X-rays, X-rays can do a lot of damage to tissue. Radiation poisoning is a very dangerous thing, and that's what this is radiation. And that's why when you have an X-ray done, you wear the lead bib to make sure the body isn't absorbing more radiation than it should be. MRI, on the other hand, does not produce any permanent damage, so that's a big plus for MRIs. So MRI doesn't have that problem. So let's call this sort of a thing to remember, number one. Now, the second thing is, so why not just use MRI for everything? The problem is MRI is inherently very expensive. And the reason it's very expensive is that the magnetic field that you need to apply to the body is very high. You need a huge magnetic field. Remember that I said a Tesla of magnetic field it's a very big unit, so 1 Tesla is a lot. Normally the fields that they use are somewhere between about 0.3 Tesla to about 5 Tesla. Okay, so there's a big range. And producing this magnetic field is expensive because how do you produce a magnetic field like that? You produce it with a solenoid. And if you remember the rules for solenoids creating magnetic fields, that solenoid has to have a very high current. So it requires a super high current. And you can only produce this super high current if your conductor is a superconductor, essentially with zero resistance. And so one thing that I was very surprised to learn about MRI machines is that I figured, you turn off when you leave for the night, you turn off the current in the MRI machine and that turns off the magnetic field. These MRI machines have to be run constantly because in order to produce the superconductors, you have to get that conducting material down close to absolute zero. That's a requirement of superconductors. And because the current is so high, you can't ever make that current go away without a huge cost of producing that current again. So, for example, if you turn off an MRI machine, the cost of getting it back up to running again is somewhere around a quarter of the total price of the MRI machine. So you have to keep it running all the time. And there's also, some dangers of having such high magnetic fields. For example, there are stories that you hear from time to time of people having tools too close to the MRI machine and it pulls it right into the machine and, of course, would kill anybody that's standing in the way. So that's sort of a side issue, but the expense of the MRI machine comes from the necessity of these very large currents.